Yo. Yo, yo, yo. Yo. Yo, yo, yo. Yo. Okay.
Well, this is not going to handle larger and larger numbers of grades very well at all. So we could say like grade average here and just output it here. We'll just output the average. And we'll just give it a recompile and run it. And oops, what did I forget to do? I forgot the semicolon. Forgot the semicolon. Put that in there. Recompile and run it. And I get an average of 81. And that looks correct, right? But this is not going to scale well at all. Like imagine I have a class with 200 students in it. Am I going to make 200 grade variables?
Heck yeah.
And then am I going to like write out, you know, grade 1 plus grade 2 plus grade 3 on and on to plus grade 200? Our code is going to be an absolute mess if we try to do that. So this is not a good way of dealing with a collection of data, like a group of related data. We need a better way than this. So the better way to do it, or at least one better way to do it, is with arrays. And arrays are kind of like our first data structure. They're our first way of handling a group of data in a more sensible way. And the way they work is like this. I'm going to say here int grade. Now I'm going to say open bracket, close bracket. I'm going to put a 5 in the middle. So what this does is it declares what's called an array. Now an array is a collection of data in memory that can all be addressed, that can all be accessed using this grade variable here. So what goes on is basically in memory, C has gone out and allocated space for, so what I can do is I can store data at these 5 boxes in memory. So I could say like, you know, grade 1 is like 92, or grade 0 is 92, I should say. Grade 1 is 85, grade
Oh, that's if I do this.
grade 2 is 72, grade 3 is 73, and grade 4 is maybe 95. And I could then store these values in these 5 boxes here, in these 5 positions, these 5 slots in memory for storing integers. And I could do that like this. I could say grade 0 is equal to 92. So when we do this, when we say open bracket, 0, close bracket, what I'm doing this time, this is actually different from this one here. What I'm doing this time is I'm accessing this element of the array, and I'm accessing this box in memory with this index, and I'm storing 92 into it. Then I could say like grade 1 is equal to 85. I could say grade 2 is equal to 72. Grade 3 is equal to, we'll say 73, and grade 4 is equal to, we're going to say 95. And these are our 5 positions in memory. These are our 5 boxes in memory that we're using now, and we're accessing them by their index here, 0, 1, 2, 3, and 4. And this here, this starting from 0, we call that 0 index. We'd say it's a 0 indexed array because you start counting from 0. And starting to count from 0 is actually a thing in programming. It's actually a common thing in programming. So even though it seems a bit unusual to start counting from 0, in programming, it's not that weird.
Okay.
Printf 2%d here, and I'm here. So what we're actually different
How
is
can I, like,
and I'll say /n. And so what I've got here now is I'm now outputting grade at the index I is equal to an integer here, and that integer here is going to be grade at the index I. So and then put compilation here to grade 3 is 73, grade 4 is 95. and we're programmatically the different very right out and right out total is than 5 value of printf and they
How
clear
can I
here
do...
integers long with the average afterwards after we've calculated based on the number of elements in the array. And so arrays are absolutely critical for writing programs that are going to scale to handle large amounts of data, where we have like large collections of data, whatever it is. It could be student grades, could be like employee salaries, you know, could be like city addresses, whatever it is. If we want to deal with large amounts of data, we're going to have to put them into arrays or possibly some other data structures as well, but typically something like arrays. And so just to be clear here, I can access and use these array values just like I can variables. So I could say here like grade 2 is equal to, we'll say grade 2 plus 5, and that'll change, you know, 72 to 77 by taking 72 and adding 5 to it and storing the result into grade 2. So if I do a recompile here and then run it, we see now grade 2 is 77 by the time we print it out. Okay, so I can use these here pretty much the same way I can my other variables, and that's okay as well. Another thing I should mention is how to initialize an array. So here we have like grade 5, and I've got like grade 0, 1, 2, 3, 4. There's a couple ways I can initialize an array. One way is I can say up here, equal to, and then I can say my list of grades. So I can say like 92, 85, 72, 73, 95. And what happens is that these 5 elements here, these elements of my array, that's what we call these individual pieces of data in the array. We call them array elements. Those individual elements are going to be initialized to 92, 85, 72, 73, 95 in order from 0 to 4 there. So, you know, I do a clear here, and I compile it and run it, and we're going to get the exact same result as before. So this is another way of initializing our values. Now, if I do it this way, I can actually just take out the 5 here. And I can take out the 5 there because the C compiler will be able to determine the size of this grade array here based on the number of elements I've got here, based on the number of values I've got here, right? So it can tell like, oh, they've got 5 values, so make the array of length 5. So if I save this here and I recompile it and run it, this will also work okay. Now, one thing we might wonder about is like, well, what happens if I want to increase the size of my array? Like, what if I want it to be larger than 5? Or what happens if I access values that are outside of the array length? Like, what if I try to access the value at grade array index 6? What's going to happen? So we could try some of those things and see what happens here. Like, we've got here up until index 4, right? So we could try an index that's beyond that, like grade 5 or grade 6, implying that there's like 6 or 7 elements in the array. So let's try to do it. We'll try to say grade 5 is equal to, and maybe we'll say here 100. In programming, it's always okay to just try stuff and just see what happens. It's a good way to learn. So you're not going to break things, and if you do, it's kind of okay. You know, the compiler's going to yell at you, or the program might crash, but that's okay. Not a big deal. So we'll do a clear. We'll do a compile here, and we've got a warning. It says array index 5 is past the end of the array, which contains 5 elements. And so it's giving us a warning already. Now, if we try to run it here, it actually runs okay. So what's going on there? That we got a warning, but it's running okay. So what's happening there is that we're getting a warning because C can tell. C can tell that like you've only got 5 elements here. Therefore, this grade array is only being declared with 5 elements worth of space. It can only store 5 integers. But this will actually work sometimes because the way that C allows us to access data is a lot like, let's say looser than other languages. It's a lot less restrictive than other languages. C will let us try to do things, and it won't always generate an error. It won't always crash the program when we do. But what we're doing here is considered unsafe. That's why C is giving us a warning like that. Because technically speaking, our program doesn't really control this position here in memory. So remember, all this data is ultimately stored in memory. And so what's happening when we try to access index 5 is that all this data is laid out next to each other in memory. And when we say go access grade at 5, we're actually going to access the sort of next position in memory to where our array is. And there could be anything there. There could be any data there. but we're basically taking that spot in memory and we're putting 100 there. So we're accessing data that we really shouldn't be. And this could have bad effects. And that's why we're getting the warning. But C is an interesting language in that it will let us do that. It'll actually let us get away with that. And it just sort of trusts us to know what we're doing. So just be aware of that you can kind of do things with arrays like this, like go outside of the index bounds, go outside of the length of the array. And C might let you do that in terms of compiling the program, but you shouldn't do that in most cases unless you really know what you're doing, because you're probably accessing memory that you really shouldn't be accessing. So just be aware of that as well. So we could make arrays of any type we like. We can make float arrays and double arrays, but one special kind of array is a type of car array. So if we have a car array like this, we're gonna say here, car, and we'll say maybe my data is equal to, we'll say 5. I'm going to say my data at 0 here is equal to A. I'll see my data at 1 is equal to B. My data at 2 is equal to C.
Yeah.
And my data...
So this is a pointer. Okay, what if I do this? Oh, let me. Oh, I forgot to delete all that. Never mind. Let me delete all this. I didn't even call that function, did I? Okay, something's not right. Am I in the right one? Oh, I called yeet instead of yeet 2. 100. So it just gave me the first one. What if I do this? Is that gonna give me? It's gonna be like, what the hell? If I do this, then it should be fine. Yeah. No, you can't print out the whole thing. But you can do a for loop and do it. Which I'm gonna do. I have to do S. That's gonna be like, no, you can't do that. Can I do I? Does I do the same thing? Yeah. Why can't I have the list?
data at 3 is equal to D. And what we've got here now is a sequence of characters in memory. So we've got something that looks like this. We've got like here in memory, my data, and we have indexes. So we have the 5 indexes again, same as we had last time. So we're gonna have here like 0, 1, 2, 3, and 4 in memory, right? And at index 0 here, we're gonna have stored A, and then we're gonna have stored at index 1B, and then in %D is equal to %C, we'll output I, we'll output S1 at I. So we're doing what we've done in the past, which is outputting each element in the array, and we're outputting the index here according to the counter variable I, according to its current value. And then we're outputting the actual value here, the actual character here individually by accessing the array at each index. And we'll just throw a /n in there to get them on a new line. And so we could do a recompilation, we could run it, and we get here, you know, S1 is 0, S1 at 0 is T, S1 at 1 is H, S1 at 2 is I, S1 at 3 is S. And that makes sense, right? Because we have this as our first characters in the string there. Then we have a space character, so we can't really see it. And then if we keep going down, you know, we're going to get to, you know, my string at the end here, and that's it. And we could do a printf of the entire string at once. So we could say printf/n %s/n. And here what we're doing is we're putting in a new line. Then we're saying we're going to give you a string as an argument, and then a new line. And we're going to print S1 then, and we should get this is my string all printed out together. So do a recompile, run it, and we get this is my string all together there at the end. Now, you'll notice that we didn't go up to the null terminator. So there's 18 characters here, but there's going to be a 19th character because of the null terminator, right? If I change this to 19 to go all the way up to that 19th character, remember that it's 0 indexed, right? So 0 up until 18 is going to be 19 characters. So if I were to go up to that 19th character, which is index 18, I get this. I get S1 at 17 is period. So S1 at 17 being period is not too confusing. But S1 at 18 is nothing. That's supposed to be the null terminator. What's going on there? So what's going on there is the null terminator is a non-printable character. So you can't actually see it. We could kind of force it though. We could kind of get around that here. So I'm going to make a loop body here now, a proper loop body. And I'm going to say here if S1 at I is equal to the null terminator. So this \0, that's the null terminator. It's a special character, even though it looks like it's 2 characters, and we've got like a single quote here, which makes us wonder, well, can we really do that if there's 2 characters here? I thought for, you know, single quotes, we could only have 1 character defined. Well, this \0, even though it looks like 2 characters, like /n, it's really stored as 1 character, as 1 piece of data. This actually is valid because that's really just 1 character. And so we're going to say that if we've encountered the null terminator, which is going to happen when I is 18, right? Let's print it out especially. We're going to say here printf, and we'll say here null terminator. We'll say S1 %D is equal to, we'll say NT for null terminator here. And I'll say here I. Otherwise, do the regular printf. So otherwise, do the regular printf where we're just going to print out the character as we did before. So we could clear this here, do a recompile and run it. And now you can see that, yes, when we did reach the 18th character, we were able to detect that that was in fact the null terminator. And we print out, you know, that character in a special way here. We say S1 at %D is equal to, we put an NT for null terminator. So we could have done this instead. We could have said \0, and that would print out \0. So \/ is a special character in C strings, and it's used to do special things like print out a new line or things like a tab as well with /t, that'll give you a tab. And so if we actually want to print out \/ and not use it as a special character, you say \\\. That's just the thing. People always forget too. This is I always forget. So \/ is this character, / is this character. I always forget that personally. So anyways, so \\, that'll give us a \, and then a 0. And that would be a way of like actually printing this out on the screen. So we'll just do a clear and a recompile, and you see we actually get \0 printed out there as well. So, you know, that's processing a string. Now, one thing that would be really nice is what if we could determine the length of a string? So right now, we're just sort of knowing that the string is 19 characters. We just know it because we just looked at it and we literally counted it out, right? That it was 19 characters when you include the null terminator. What if you don't know the length of the string you're dealing with? And that's something that might happen, right? Because maybe the user gives us a string, and maybe we don't know the length of the string. So, what if we got something like this? What if I say here, I'm going to say here car, and I'm going to say here S1 is equal to, let's say 20 this time. Then I'll say printf enter to ask the user to enter a string, and I'll say scanf %s. Now here, instead of saying and S1, I'm just going to say S1. And what this is going to do is it's going to read in a string and store it into S1. And it will put the null terminator on there for us. Now, I don't put the and there, which is interesting. We're going to have to explain that later though, because that involves a bit of a more tricky concept called pointers. Now, we're just going to put S1 there, and it is going to store the string that we put in into S1. And then what I'll do is I'll do a printf of S1 just to make sure we've got it correctly. So I'll say here S1 %s/n, and we'll output it just to make sure we've gotten it okay. So we'll do a clear here now, and we'll just do a recompile here and run it. So it says enter. I'm going to say my string here, and I get S1 my string here. I could say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, what's happening here? Because I've got this character array that can store up to 20 characters, and yet in the case here, you can tell that's clearly not 20 characters. There's only 10 characters there. So even if we include the null terminator, we've still only got 11 characters, right? So we can store strings into character arrays that are larger than the string itself. So we could loop through this string here, and I could say for int I is equal to 0, I is less than, we'll say 20, I++, and we could do a printf of all 20 positions in S1. We could say here S1 %d is equal to %c, and we're going to output each position, each index in S1 here and its value. And if we were to recompile it here and we run it, we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll see here we get this data here from 0 to 9. We get that S1 here is going to be the null terminator. We can't see it because we're not doing the special thing to print it out, but we know that's going to be the null terminator. And then the rest of the array is available to be used. You can tell there's some junk data in it. So we warned you about that. We said that if we don't actually initialize our variables in C, there could be junk data in them. So there's some junk data in there. Cool. But this means we can store things of varying length into S1. So I could say ./d, and I could say enter. And this time I'll say 0, 1, 2, 3, 4. And now you can tell that I've got 0, 1, 2, 3, 4 stored in there. That's going to be the null terminator, and the rest of it's blank. And I could say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0, 1, 2, 3. And we've got now 0 to 9 stored in there, and then 0, 1, 2, 3, and then that'll be the null terminator there. So what's going on here is interesting for a few reasons. One is we can store strings of varying length into a character array. And what really makes the end of a string is not the length of the character array. What really signifies the end of a string is the null terminator being there. So we could write code to work with strings based on the null terminator being there. That could be one way we do things. So we could say something like this. We could say here int I is equal to 0. And let's say we want to print out any zeros in the string. So anytime we find a 0, we're going to print out that we found a 0 in the string. So what we could say is this. We could say while S1 at I doesn't equal the null terminator, keep going. And so long as S1 at I doesn't equal the null terminator, we're going to keep going. And we're going to say here if S1 at I is equal to the character 0, we're going to printf found 0. And we'll just printf found 0 like that. And then we're also going to increment I each time in this loop here. So we'll say here I++. Okay? And then we can then find how many zeros we've got in our string by looping through it one character at a time until we encounter the null terminator here. So let's just give this one a try. We'll say clear do a recompile, run it, and I'll put in like 0, 1, 1, 1, 0, 5, 0, 2. So there's 3 zeros in there, so we expect to be seeing found 0 3 times. And we get found 0 3 times, then we get S1, and we get the rest of the string here. So if I want to process a string one character at a time like this to maybe search it for certain information or whatever it is I want to do with the string in terms of processing it, I could use the null terminator like this as a way of signifying the end of the string. And then if I want to give strings of different length, I could do that. So I could say here like 1, 2, 3, 0. I'm only going to get found 0 once. But this string is a different length than this string. And yet I'm able to process that okay with this loop. Not really working with the length of the string. Really what I'm working with is the fact that we know that strings end with the null terminator. And so I go from 0.
Mine didn't work. I wonder if it's because of this. Did I do something wrong?
Incrementing by 1 through each character of the string here, and we know that we're done when that character at I there.
Oh wait, is it? Yeah. Oh, it'll stop before it's asking.
Is the null terminator. Now, with strings, some things can get messy just because of the fact that they are ended with the null terminator and not with, say, like a, array of a given length or something like that. So we could say here, let's run it here now. I'm going to say here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm about to put in 30 characters, but my character array here only stores 20. And look what happens. Abort trap 6. And we did get like found 3 zeros here, and we did print out S1 here successfully. We get this abort trap 6. So we're not going to get particularly good behaviors if we don't respect the fact that our arrays can only store strings of a certain length safely. So now what we're doing here with checking for the null terminator, this will work, but there's other ways of working with strings. So strings are such a common thing to use in C and really a lot of languages out there that they give you another library. So this stdio.h library, pretty much every C program you ever write will include that because you're pretty much always going to want to print things to the screen and things like that. Now, another common library to include is the string.h library. So we're going to say here include string.h. So string.h is another library that comes with C. So like stdio.h comes with C, string.h comes with C, and you're always going to have access to it, and the compiler is going to know where it is and how to include it. Now, what string.h gives us is a bunch of functions for working with strings. Now, it would take too long to go over all of them, and I post different videos going over each of the functions individually and things like that on my YouTube channel. So I'd actually point you towards those. But let's actually go over some of them here. So let's make a string here now. We'll say here car S1. And I'm going to say it's equal to this is the way. So the string is this is the way here. And then what we could do is we could get the length of the string. So I could say here like int length is equal to, and I'm going to say strlen s1. So strlen,
Okay.
that's a function that comes with string.h.
Yeah.
And if we include it, we have access to it. And what it does is it finds the length of the string. And it finds the length of the string without the null terminator. So it doesn't include the null terminator in the length of the string. So in the case of this string here, we expect it to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 characters long. So I could say printf here, length. And then we could output the length of the string here. So I'll say clear, do a recompile, and run it, and we get length 16. So then instead of writing a loop that works based on the null terminator being found, we could write a loop that works based on the length here. So we could say here like for int I is equal to 0, I is less than the length, I plus plus, and we could do a printf here, or we could have it do some work. Like maybe we're gonna have it count the number of i's in the string. So we could say like here int num i's is equal to 0. And then we'll say here like if the s1 string at I is equal to
What am I doing? Why am I?
do the character I, then we're going to increment num i's by
Oh,
1.
shit.
And then we'll do a printf here with the number of i's. So we'll say like number of i's, we'll say %d/n, and then we'll say here num i's. Okay, we'll do a recompile here. We run it, and we get the number of i's is 2, and that makes sense because there's 2 i's in there, right? And we could change it to another character like say h, and there'd be 2 h's in there. Or we could change it to say w, and we'd only expect 1 w. So we could say like num w. We'll say num w's now. Just to be consistent here, we'll change it to num w's everywhere. So we'll say number of w's now, and we should only find 1 w now. And we find 1 w. So we could write then loops to work with our strings that are going to maybe look at each character and do some kind of analysis, like counting the occurrences of a certain number of characters or something like that. And we can do it now based on the length of the string as opposed to, you know, searching for the null terminator. Now, there's all kinds of functions that come with string.h. Another one that's interesting is called string_cat, and this does string concatenation. So we could say here, I'm going to say here car s1, and I'm going to say here 50 is equal to the first sentence. And then we could output the length of the string here. So I'll say clear, and we should only find 1 w now.
I'll change it to W. I don't know why it doesn't use brackets, because that's annoying, yeah. Okay.
Now. And we find 1 w. So we could
This is
write then
Python, bro. You have
loops
brackets.
to work with our strings
Yes.
that are going to maybe look at each character and do some kind of analysis, like counting the occurrences of a certain number of characters or something like that. And we can do it now based on the length of the string as opposed to, searching for the null terminator. Now, there's all kinds of functions that come with string.h. Another one that's interesting is called string_cat, and this does string concatenation. So we could say here, I'm going to say here car S1, and I'm going to say here 50 is equal to the first sentence.
Notes.
Every legendary course begins as a vision.
Quick break.
Hi, my name's Luke. I'm an indie dev with a terrible golf swing, and this is normal golf game. This isn't like other golf games where you just tap a few buttons to swing. Instead, you drag your hands around with physics while simultaneously balancing the angle and path of the club face. You have complete... Wait a sec here. Why you would have agreed to give me all of your money, or if you can leave. You are free to explore the course and complete all kinds of very normal challenges. You can shoot from anywhere, at anything. At some point you might start thinking, what's the point of all of this? Why must I play golf? I do not recommend thinking about it too hard. After all, what's day out in...
Oh my god. I don't know why I'm community manager on this game.
I don't want my money back. I want the time back I wasted in this game. The amount of stress and time it worried more than is worth more than every penny. Okay. This is it. 70.
No one else is listening. It takes my good times, me another time. Doing alright from you. You're never there. Look away.
Julie, do you feel real? Cutting coattails behind my mouth. Supercilious, kick your feet up. Riding corners, convey a smile. Slightly altered, not how you spun it. Do you ever see behind my mouth? Do you ever see behind my mouth? Do you ever see behind my mouth? Buckled under, unlikely pleasure. Do you ever see behind my mouth?
Then I'm going to say here car S2 is equal to the second sentence. So what I've got here is two strings, the first sentence and the second sentence. And this is going to store this string into S1. This is going to store this string into S2. Now for S1, I deliberately made the array much larger than necessary to store this string. In fact, it's big enough that it could actually store both strings. And that's because I'm going to use the strcat function to concatenate the strings. And so the strcat function, the string concatenation function, is going to concatenate the strings. It's basically going to append this string to the end of this string. So we'll call it here, I'm going to say strcat, then I'm going to say s1, s2. And what this does is it takes this string here and it concatenates it on to the end of this string here. So it basically kind of takes off the null terminator from the end of this string and then puts this string from that position onwards. So then if I do a printf of S1 after doing this, we're going to get the first sentence and the second sentence. So I'll do a clear here, do a recompile and run it, and we get the first sentence and the second sentence, one after the other, because this function here concatenated this string onto the end of this string here.
Whoa.
Now for that to work, it was really important that this array here was large enough to hold both strings. If that didn't work, it would be a bad time again, right? It'd be things that we don't want to happen would happen.
Oh, no,
Now, there's all kinds of functions in string.h for manipulating strings as well as comparing strings. And I'll just show you one more because, like I said, there's just too many functions to show you all of them. And I'll leave those for other videos and your own sort of research.
Take it. Why can't I? Dude, everything's so complicated in this. It's like insane. Okay. Okay. You know what? Well, alright, it's an int. What's it gonna print? Okay, okay. -64. What the hell? Okay. So is it like a pointer? I think I got it. No. How is that an int? Oh, if I make this a pointer, give me the addresses. Oh, yeah, it's gonna be like, what the hell are you doing? I get a bunch of errors now. It's just chaos. Alright, I'm gonna ask ChatGPT because I'm like, what the hell? How do I do this? No, wrong project. Why no work? I guess I can check the man pages. Why am I still in Maine? Ugh. Oh, yay. Oops. Alright, is this gonna work? Aha. This function can ask a string pointed to by source, separate string pointed to by destination, I'm assuming. I'm so confused. a pointer. So this should work then. How's that an int? It's a pointer. Oh, I'm so dumb. Ah. really hate this, bro. C is so dumb. Let's go back to Python. Frick. pointers, bro. Oh my gosh, bro. Should be illegal. Whoa, you got me there. You got me there, Claude. One of the same is not like the other. I'm the retard. Don't worry. I'm still retarded, bro.
So what I'll say here is car S1 is equal to, and I'll say this is a string. Then I'm going to say car S2, and I'm going to say this is a string. If I want to compare two strings for equality to see if the characters in one string match the characters in the other string at each index in the string, that's what strc.
Wait, let me find which one. Oh, I forget which one. String diff or something.
CMP can do. It compares two strings, and it'll return 0 if they're equal. So I could say, like, if strcmp s1 s2.
Calm down, boy. Oh, string. Yeah. Okay. This will return 0 if let me do this because it should return 0, right? That returns 0. So they are not, they are the same. Whoa. So negative 49. Does it matter what I put in this string? No, I just chose 49 as the fail code. So it's an array, like, okay, it's like, how do you make a string? A string, one string is an array of characters. So that's why. So if you want an array of arrays, it's basically an array of characters of an array of characters. Okay. Okay, I'm starting to get some stuff. So let me write a function here. If oh, I ain't even gonna do that. If we'll actually no, I'm gonna do printf. Strings are not the same. Dun dun dun. And just do else. Oops. Yep.
In this video, I'm going to go over struct 2 is equal to 0. We could do a printf and we could say S1 and S2 are equal. And this will determine if they're equal. So we could do a clear here, do a recompile, run it, and we get S1 and S2 are equal. If there was something different about them, like if I had a character A here instead of, if I had a capital case A there instead of a
If
lower.
I do man. What does it say? It'll return 0. Interesting.
Lowercase a there, then what's going to happen is S1 and S2
This
are
one
not
should be
equal.
greater. So it should give me.
So we could run this now,
Yeah,
and
plus 49.
we'll just say like aren't equal here. Aren't equal. Okay, do a recompile here, run it, and we get S1 and S2 aren't equal there. And that's because there's a difference. Like this is a capital A, that's going to use plus here, and false otherwise. We're going to print out upper. If it's a lowercase character, we're going to print out lower. And if it's neither, we'll just throw on a new line. And then this will give us a printout of all the characters in the string. And And as we write programs that are larger and larger, it's going to turn out that we really do need to split them up into functions. And what we're going to do is we're going to create and use
so
our
just the
own
main
functions.
function.
And that actually really becomes necessary for a couple reasons, really. One is just that it's not practical to write all of our code for a complex program in the main function. At a certain point, we just sort of can't really think about or debug or read our program if we just have, say, like tens of thousands of lines in the main function. At a certain point, what we're going to want to do in order to make our programs comprehensible and understandable as a reader is to decompose them and to split them up into different functionalities that we then access as functions. And it's going to turn out, actually, if we go really far into programming, we keep going, that eventually we're going to make our own libraries of functions. We're going to make our own collections of functions. So in the same way we've got like the string library here, eventually what you'd end up doing is make your own libraries of functions and group together functions with a common purpose into a library. Now, what we're going to talk about in this little mini course here is how to make our own functions, because that's the first step, is we got to know how to make our own individual functions. So let's cover that now. Let's actually make and use our own functions. Now, another reason why we might use a function is because there's some task, there's some functionality that we want to carry out in different sections of our code. So finding the maximum of two numbers is not too tricky, right? Like if we have two numbers, we say int a is equal to 5, int b is equal to 10. If I want to find the max number between a and b, I can just throw an if statement in. I can say if, a is greater than b, we'll say that max is a. So we could say like int max is equal to 0, and we'll set max to a if a is greater than b. So we'll say max is equal to a, and then we'll say else max is equal to b. So if a is greater than b, we'll set max equal to a. Otherwise, we're going to set max equal to b here, right? And this is just a little two-line if statement here, right? But if I needed to do this everywhere in my code that I want to find a maximum number, that's going to get pretty repetitive. It's the same thing over and over, right? And it's going to increase the size of our code relative to just being able to say max AB and just getting a max value in return and setting it equal to max here. So we could say like maybe call it find max or something like that, right? We can make a function called find max that finds the max between A and B and returns the value. This is only one line of code. And it's pretty simple to understand what's going on here, that this would find the max between A and B and return that maximum value. So this is already shorter, and we're only talking about functionality that is very trivial, like finding a max number, very trivial functionality. Now imagine we have like 100 lines of code that does something, maybe does something more involved, like takes two strings and finds the words that are most common between the two strings, and so it's a more involved function, right? Something like that. Imagine we've got to put the code for that all over the place in our code. That's going to be a mess. So what makes far more sense is that for these sort of things that we want to repeatedly do all over the place in our code, we package them together in a function that we can just sort of call to carry out that functionality. So let's go over how to make and use one of these functions here. So the first thing we'll do is we'll create a function here. I'm going to make a function called findMax, and at first I'm going to make it up here. I'm going to say int, and I'm going to say findMax. Now I'm going to say here int a and int b. So what this is this is my first function here, and this is the function name. So that's the name of the function. These are called the parameters of the function. So these are basically variables that are going to be local to this function. So these are variables that I'm going to be able to use and access inside this function, in the same way that when I had like int I with my for loop, and I was then able to access the integer I inside the for loop. Same idea with these, where A and B are going to be accessible inside the block of the function in the same way I here is accessible in the block of the for loop here. And so these are going to be parameters, they're called. But what's going to happen is when I call the function, I'm going to pass it specific arguments.
Okay.
So I'm going to give the function specific arguments.
Getting the pointers
And
in.
A and B are going to be set to those argument values, to those specific values. Here, int max is equal to find max, and I'm going to say here 10 and 5. Now 10 and 5, these are considered arguments. So these are things that I'm passing to find max. we would say that I'm passing the values 10 and 5 to find max. And when find max executes, the control flow is going to jump up here now. The control flow is going to jump into this function now. And when find max executes, A is going to be set to 10 and B is going to be set to 5, because that's the argument values I've got here. I've got 10 and 5, so A is going to be set to 10, B is going to be set to 5. Then we're going to check, is A greater than B? Yes, it is, right? So we're going to return A. And at that point, what's going to happen is this function call here is basically going to evaluate to the value 10, because that's the max value between the two. And then max will be set to 10. And so when we call a function control flow, the execution of statements is going to jump to that function, and it's going to start executing the statements in that function until it encounters a return value in the case of a function like this that is returning a value. So this function here is returning a value, and so the expectation here is that the function will eventually have a return and then some value here. And so we could then say printf max, and we could printf the max value that's returned. So we could say max %d /n, and I'll print out max, and we'll see what we get. We should get 10, but we'll just give it a try here. So I'll say clear, do a recompile and run it, and we get max of 10. Now if I change this to 12 here, I'm going to get a max of 12 if I do a recompile and run it. And what's going on there is that, again, the function is called. This time, though, A is going to be set to 10, B is going to be set to 12. The statements in the function are then going to execute with that assumption, with those values, right? And so we're going to get now that, 10 is not greater than B. This is going to be false. So we go down here to the else case, and we return B, which is set to 12, and that's why we get 12 back from this function call. And that value gets assigned to max, and then we print it out. And so that's the basic idea behind a function, is that we call it to do some work, and typically a function will return a value. Doesn't have to. I'll show you in a second an example of one that doesn't. But it doesn't have to return a value, but it typically does. And when it returns a value, we actually use it here and in an assignment, and we assign that value to max. Now we could use the value returned by the function in an expression. So we could say something like int, we could say here result is equal to find max, and we'll say plus 10. And this should take 12 then and add 10 to it. And we could say, let's print out result now. And we're going to get here, we should get back 22, right? Because we're going to take 12 as the max value here. And then we're going to add 10 to it. So we should get back 22 now for a result. So we can run it there, and we get back 22. So we can use the return value that we're going to get from calling the function however we like, really, in an expression, and that's fine. One thing that's important to understand is how variables work when we call a function. So we need to talk about what's called variable scope. So variable scope is basically where a variable exists and which variable will be accessed when we actually go to use a variable name. So for example here, the result variable, because it's declared inside of this block here, it exists within this block. And so we actually can't use the result variable inside of find max. Let's see what happens if I try that. If I try to say here printf, and I'll say, let's say result, %d /n result. We'll try to print out result. This is not going to go well. So I'll do a clear here, I'll do a compile, and I get error, use of undeclared identifier result. And it's pointing me towards that exact line there. And what's going on here is that the result variable, the one that I'm using right here, just doesn't exist inside of find max. It just is not a thing there. Same thing with A and B. So A and B, those are called parameters, and parameters have the scope of this function here. And therefore we can't use A and B in main. So if I try to say like printf, and I say like A %d, and I'll say B %d, and then I'll try to print out A and B, we're gonna get a similar thing here. It's not gonna go very well. If I do a clear, I do a recompile, we get two errors now. We get like error use of undeclared identifier A, and we get error use of undeclared identifier B. So these variables here, we would say that they have local scope or they have function level scope. So like A and B, they have the local scope of this function here. We would say they have function scope. You could say local scope or function scope. People will know what you mean if you use those terms. The result variable here, same thing. It has function scope. It has the scope of the main function. In other words, it can be seen in the main function. It also has what we call like local scope. So you could say local scope 2, same idea. Now with variables, so long as we're just sort of mentioning this, we can't use them before they've been declared. So I can't use result up here. I couldn't say like printf result before it's been declared. That also will not work. So long as we're talking about variable scope, we might as well talk about that. So one thing we've got here is we've got the find max function defined above main. Now typically this is not what you do when you're writing a C program. And the reason is if we've got like maybe let's say 12 or 20 or 30 functions defined in this file, we've got to then scroll down quite a bit to find main, right? Because it's going to be kind of buried underneath all those function definitions. And so what you actually typically see is the function definition split up into two parts. What's called a function declaration and then a function definition. So we can split it up like this. I'm actually going to take this here, I'm going to copy it, but here I'm going to leave one little piece. I'm going to say semicolon, and I'm going to delete the function body here. We call this the function body. I'm going to delete that. And I'm going to leave this here. We call this the function definition, and this is defining what the find max function is. It's saying that the find max function is going to accept two int values as parameters, as arguments, and it's going to return an int value. And this is the function definition. It basically tells the C compiler that yes, when you see the find max function being called, it's okay to use it because the definition for that function is going to be provided later. Then down here, what we do is we provide the definition. So down here, we provide the definition for the function, and we define find max, we give the function body. So we repeat this same sort of function prototype it's called here, the function declaration here. We basically repeat the same information from the function declaration, and we then provide also the function body at that point. And this is actually considered the more normal format for defining functions in a C program. So we can clear this and compile it and run it, and we'll get the same result as before. And all that's happened is we've split it up. And the idea here is that I could then have like, maybe let's say like, 10 definitions here, but I don't have to scroll down too far to find the main function, which is probably the thing I want. And we'll get the same, and it basically tells this will not work. So long as we're talking about variable scope, we might as well talk about that. So one thing we've got, and it basically tells the C, and we'll get the same result. Function, take the declaration, and then a function definition. So we can split it up like this. I'm actually going to take this here, I'm going to copy it, but here I'm going to leave one little piece. I'm going to say semicolon, and I'm going to delete the function body here. We call this the function body. I'm going to delete that. And I'm going to leave this here. We call this the function definition, and this is defining what the find max function is. It's saying that the find max function is going to accept two int values as parameters, as arguments, and it's going to return an int value. And this is the function definition. It basically tells the C compiler that yes, when you see the find max function being called, it's okay to use it because the definition for that function is going to be provided later. Then down here, what we do is we provide the definition. So down here, we provide the definition for the function, and we define find max, we give the function body. So we repeat this same sort of function prototype it's called here, the function declaration here. We basically repeat the same information from the function declaration, and we then provide also the function body at that point. And this is actually considered the more normal format for defining functions in a C program. So we can clear this and compile it and run it, and we'll get the same result as before. And all that's happened is we've split it up. And the idea here is that I could then have like, maybe let's say like, 10 definitions here, but I don't have to scroll down too far to find the main function, which is probably the thing I want to look at first. And then if I do want to look at any one of these function definitions, I can always find it in the file down here. And so this is actually the typical style to be used when you're actually creating functions in a C program. So it's very important that we understand the relationship between these arguments here and these parameters here. So let's go over an example to do that, just to make sure we understand it, because if we don't, we could really run into trouble with our program logic and being able to figure out what's going on. So I'm going to make a function that's going to triple a float value. So I'm going to say here float triple, and it's going to triple the float value that it's given. So I'll say here float n. And there's my function declaration. Now let's provide the definition down here. I'll say float triple, and what I'm going to say here is n is equal to n times 3. Then I'm going to return 0 here. So I'm tripling the number, right? I'm taking n and I'm multiplying it by 3, and I'm storing the result in n. And I can just return 0, right? Because I've already tripled the number. And then what I'll do here is I'll say here float x is equal to 5, and then I'll call triple. I'll say triple x, and then I'll print fx just so we can see it after we're done. So I'll just say printf and let's just print f what we get for x now. And I expect that we should get, 5 times 3 is going to be 15. So I'll clear this here. I run it, and I get 5. So what's going on here? So what's going on here is that what is passed to the triple function is not x. It's not like we're passing like x on some kind of deep level where then n is really able to then modify x. What's actually happening is that the value of x is being passed, and the value of x is 5.0. So it's actually as if we had done this. It's as if we had passed in 5.0 here. And this variable here, n, it has no relationship to x, other than the fact that it gets passed that value. It's not like it's somehow tied to x, so that when we modify n, we're going to modify x. And it's really important that we understand that distinction here. So we can pass it x, but what we're going to have to do to modify x is return n here. Because at this point, when the function runs, n is set to whatever the value of x was, which is 5.0. And then from that point on, n has nothing to do with x. So we say, n is equal to n times 3, we can modify n, and then we can return n, and that's fine, but unless we actually take this return value and use it in an assignment statement, it's not like it's going to modify x. So we'd have to say like x is equal to triple x to actually have it modify x. So we can compile it here and run it. And now we get x15. Functions can also have their own local variables. So I can make a function here called add. So
done for today.